Swayam Prabha. Digital India. Educated India.
We'll continue the discussion on the Benard-Marangoni instability in this lecture. So in the previous lecture, we had looked at, starting from the governing equations, we had derived the non-dimensional form of the Buzynski equations. These are on your screen. So the problem setup was we have a hot plate at the bottom and we have a liquid of thickness D. We will assume that the gas above is passive. We had non-dimensionalized the equations by introducing a temperature variable theta, which is defined as the temperature, relative temperature in the bulk relative to the hot plate at the bottom, divided by the maximum variation possible, which is T1 minus T0. Now theta as a result goes between 0 to 1. During the process of non-dimensionalization, we also encountered two non-dimensional parameters. The Prandtl number, which is a ratio of kinematic viscosity to thermal diffusivity. It tells us how fast does momentum diffuse in the fluid relative to diffusion of temperature field. Similarly, we have a Grashof number, which tells us the ratio of buoyancy forces to viscous forces. Now what we're going to do in this lecture is to first obtain the base state problem. Okay, that is when there is no motion in the flow, and then we'll perturb that base state and we'll derive linearized equations. So let us proceed by first looking at the base state. So the equations in non-dimensional form are written here. These are already derived in the previous lecture. So let's write down the base state. So what we now are looking for is a steady state solution. This would happen when there is no motion at all in the flow. The velocity field is 0. And if you look at the temperature equation, simplifies to del square of theta is 0, right? Further, there are no variations in x or y. All the variations will be in z, and therefore this essentially becomes d square theta by d z square is 0. Now we need two boundary conditions. Recall that the temperature at the bottom at the dimensional location, the temperature at the bottom, the dimensional temperature was T1, and this implies theta is 0. The definition of theta, again, let me write it here on the side. Theta would be T1 minus T tilde divided by T1 minus T naught. So the temperature is T1, theta is 0, and at Z is equal to D, or in other words, non-dimensional Z is 1. The temperature T was T naught, and this essentially gives us theta equals 1. So we have now this equation. We can integrate this equation. D square theta by dz square is equal to 0. If I integrate it, I get d theta by dz is some constant c1, and theta as a function of z will be c1z plus c2. If you substitute the condition at z is equal to 0, you get c2 to be 0. And if you substitute the condition at theta equals at z equal to 1, then you get theta will be c1 will become equal to 1. And therefore we get, using boundary conditions, at z is equal to 0 and z is equal to 1, we get the non-dimensional temperature distribution will be just z. So the problem that we have now is a hot plate and an interface. So the hot plate is at z is equal to 0, the interface is at z is equal to 1. Then we have a temperature distribution which is the temperature distribution which is linear. Okay, this is theta versus z, where z is vertically up. Remember, this is theta, so theta is t tilde minus t minus t1 minus t0. So theta will be 0 at the bottom. Don't look at this profile and think that the temperature is actually increasing as you go to interface. On the contrary, the temperature is decreasing. If I were to plot the dimensional temperature, the dimensional temperature would be something like this. So at the bottom we would have T1, at the top you would have T0. Okay, and it would decrease linearly with distance. Okay, so now that we have this base state, so now if, we can actually use this temperature to substitute into the momentum equation. If you look at the momentum equation, the left hand side would be identically 0. Let's label these equations. Let's call this as 1 and 2 and 3, and this result that we've just now got, we call it as 4. If we substitute this result number 4, that will be equation 4, into the equation 2, which is the momentum equation, notice that all the terms will cancel out except two terms, the pressure term and the buoyancy term. So the pressure essentially becomes, from 2 we have the pressure, which I'll call it as delta P bar, will be GR 1 minus Z Ez. So the base state that we have, or base state or the basic state that we have, is u bar is 0, theta, which is theta bar. So essentially we can say u bar is equal to u bar mean. So the overhead bar indicates it's a base state quantity. Theta bar, which is Z, and finally the pressure gradient is the base state pressure gradient would be 1 minus Z Ez. That's the base state pressure gradient. Okay, so now what we want to do is we want to perturb the base state. Now, we have three velocity fields, three velocity components, u, v and z. So the perturbation for u will be u bar plus epsilon u hat, epsilon v hat, epsilon w hat. So I'm just writing down the components like this. So left hand is a vector. So the u component is perturbed by a perturbation epsilon u hat, the v component by epsilon v hat, and the w component by epsilon w hat. But we know that the mean is 0. So essentially my velocity field that I have now is only the perturbation, that is u hat, v hat and w hat. Remember, this is u hat, v hat, w hat are the scalar components of the perturbation. Scalar components of the perturbation. So similarly, I can do the same thing for other quantities such as theta, I can say theta will be a theta mean plus an epsilon theta fluctuation, and the pressure will be a pressure mean plus an epsilon times pressure fluctuation. So let's now derive the linearized equations. Okay, so all velocity components are order epsilon, right? Because you can clearly see that there is no mean flow, there is only a perturbation epsilon velocity components. So therefore implies terms like u dot grad u, all terms which are basically, you will have 9 terms here like u dot grad u, because u is a vector. This quantity here essentially will be, all these terms will be order epsilon square, and hence they are small. Okay, can be ignored. So let's write down the linearized equations. Meaning only order epsilon terms are considered. We don't have terms smaller than order epsilon. We also don't need to consider the base state, as it cancels out the mean with the mean. Okay, so the continuity equation essentially becomes, all that we do is we're substituting these perturbations into our equations 1, 2 and 3. Okay, so what we now have is the continuity equation becomes del u by del x, del v hat by del y by del z is 0. Note that there is no epsilon because epsilon will cancel throughout. Okay, so we have this. Now we have let's write down the temperature equation. We have del theta by del t. Now again notice that the convective terms that we have here, that I'm highlighting now, this is order epsilon, right? And then you have this theta will be theta mean plus perturbation epsilon theta hat, right? So there is a mean quantity as well. So these terms will enter the discussion. So what are the quantities that we have here? We have, if you substitute this, we have u hat del theta by del x plus v hat del theta by del y plus w hat del theta by del z, right? But if you notice again, I will delete some of these terms here. Del theta by del x, these are all nonlinear terms. These are all these terms are order epsilon square terms, can be neglected. So we will not have any of these terms here. But what about the mean? Okay, so the mean quantities would be u hat del theta bar by del x plus v hat del theta bar by del y plus w hat del theta bar by del z. Now clearly, if you look at it again here, these terms is 0. This is 0 because the mean does not have any variation in x nor any variation in y, and the variation in z will be exactly equal to 1 because theta bar is exactly equal to z, and therefore del theta by del z is unity. So I will erase all of this and simply write down the final expression that we have here. What we now have is plus w bar times 1, w hat times 1, sorry, this becomes 1 by Prandtl number del square of theta hat. This is my temperature equation. The momentum equation that we have here, all terms involving u dot grad u, they're all 0, and therefore they're small basically. So then we have the x momentum equation. This is the only linear term on the left hand side. On the right hand side we have del p hat by del x plus del square u del v by del t will be del p hat by del y plus del square v. Both of these are the horizontal components. X and y are horizontal, parallel to the surface. And finally we have the vertical component of the momentum equation, del z plus del square w minus gr times theta hat. Okay. If you remember the equation that we have here, the equation that we had was gr times 1 minus theta, right? So this gr times 1 minus theta, if you substitute the expression for theta, theta would be just theta bar plus fluctuation. But the theta bar, if you cancel out, now if you write down the perturbation, theta is theta bar plus perturbation, and only consider the perturbation terms, meaning the base state will get cancelled with the base state pressure. So the perturbation pressure will balance the perturbation. You have the perturbation in the gravity term in the last quantity, and you have a perturbation pressure, that is del p by del z, but you also have some momentum terms, velocity terms. So now what we have is we have a combination of 5 equations and 5 unknowns. The unknowns are, we can now simplify some of these equations. Let's label these equations. We have already used the label up to label 4. So let's label them as 5, 6, 7, 8, and 9. Okay. Now we can actually do some simplifications, which we'll take a look at it now. So we can combine equations 7 and 8. Okay, so how do we do this? Now if you look at 7 and 8, these are the horizontal components. So I will take a del by del t of, so what rather, let me just do it sequentially. So we take a del by del x of equation 7, and we will add it to del by del y of equation 8. This is what we're going to do. So what we now have is, if we do this, then we get del by del t of del u hat by del x plus del v hat by del y. That's the left hand side. This becomes del p by del x. If I take a derivative of that with respect to x, we get del square p hat by del x square plus del square p hat by del y square. That's what we're going to get. And finally we're going to get del square of del u hat by del x plus del v hat by del y. This is what we have. Now we can use a shorthand notation to simplify this. Now this quantity here, if we look at the continuity equation, that's continuity equation is equation 5. Del u by del x, del u hat by del x plus del v hat by del y is minus del w hat by del z. Therefore this quantity becomes minus del w hat by del z, same as this here, minus del w hat by del z. And we will also define a new gradient operator, Laplacian operator, a horizontal Laplacian operator, which is del square by del x square plus del square by del y square. Okay, this is with the subscript 1, and therefore this equation becomes del by del t of minus del w hat by del z becomes minus del 1 square of p hat, right, plus del square of minus del w hat by del z. That's what we have now. So now what we have is we have del by del t of del w hat by del z, if I take it to the right hand side, minus del square of del w hat by del z. I take the pressure to the left hand side, I have del 1 square of p hat, and this nothing but del by del t minus del square, this is an operator, of del w hat by del z. This becomes del 1 square of p hat. This is the new equation that we have got, and we can label this equation as equation number 10. Okay. So what we have now done is we have taken the continuity equation into account, right? We've already used the continuity equation to relate the two derivatives of u and v, that is del u by del x and del v by del z, del v by del y, in terms of minus del w by del z. So we've used the continuity equation. We've also combined the two, so that's we've also combined the two momentum equations, that's 7 and 8. So basically we have essentially eliminated 3 equations, that is 5, 7 and 8, and in their place we have now one single equation. Okay, so let's write down the simplified equations again. What are the simplified equations that we have? We have the temperature equation, that is del theta by del t, del theta hat by del t, plus w hat becomes 1 by Prandtl number del square of theta hat. This was our equation 6, right? Then we have equation 9, which was del w hat by del t this was our equation 9, and finally we have equation 10, which is del by del t minus del square of del w by del z is del 1 square of p hat. This our equation 10. So now we have 3 equations and 3 unknowns. Now the unknowns are theta hat, w hat and p hat. These are my unknowns. Okay. Now we can do one more thing. We can actually combine equations 9 and 10 to eliminate pressure. Okay. Combining 9 and 10 to eliminate pressure. So how do we do this? We first differentiate this equation 10 with respect to z. Differentiate equation 10 with respect to z. The reason is, if we do this, then the p hat that we have in equation 10, now we will end up getting del p hat by del z. Now similarly, I can operate equation 9 with del 1 square operator, and then we can subtract one from the other. Okay, so what we have, if I do this, I get del by del t minus del square of del square by del z square is no square of del p hat by del z. Okay, this is one equation that I've got, and I can also do one more thing. I can operate del 1 square on equation 9. If I do this, I have on equation 9, so that is del by del t minus del square of w hat. That's my equation 9. So in other words, I'm combining the two terms that I'm highlighting here. This term and this term I have already written here. But now I have w square. Instead of w square, we get del 1 square of w hat. Okay. This essentially becomes minus del 1 square of del p hat by del z. And finally, I have the last term, which is gr del 1 square of theta hat. Now I have got two equations now. Now we can, because the pressure terms have opposite sign, I can add these two equations. If I add the above two equations, what do I have now is del by del t minus del square. The terms that we get now added for the velocities would be the first term del 1 square w hat plus del square w hat by del z square. This is what I have. The pressure term will cancel out, and finally I have del 1 square theta hat. But this term here, del 1 square, if you expand del 1 square, what was del 1 square? It was del square by del x square term plus del square by del y square term, but you also have a del square by del z square. This is simply del square of w hat. So what we now have is del by del t minus del square of w hat simply becomes gr theta hat. This is what we basically have. Okay, so we'll give this a label. We'll call this equation 11. Okay, so now basically we have only two equations. We have the equation 6, which is the linearized temperature equation, and we have equation 11. Clearly these two equations are coupled now for only two variables, right? Theta hat and w hat. Okay, so we now have just equation 6 and equation 11 for the variables theta hat and w hat. Okay, now we can do one last simplification. We'll define a parameter. I'll call it as a theta reverse hat. Okay, this theta reverse hat is nothing but theta top hat divided by Prandtl number. Okay, and it will become clear why this would well, this is not necessary. We can continue with what we have, but let's see what happens. Okay, then equation 2 simply becomes del theta by del t, essentially becomes del theta reverse hat by del t plus w normal hat is equal to del square of theta reverse hat, inverted hat, let's call that inverted hat. So we have Prandtl number del by del t minus del square of theta inverted hat is minus this. This will give it a label. We'll call this as equation 12. And if we do the same thing, I have theta hat there. If theta hat essentially becomes theta inverted by Prandtl number. Okay. So if we do that, we have equation 11 essentially becomes del by del t minus del square of del square of w hat becomes a new non-dimensional number Ra del 1 square of theta inverted hat. This is equation 13, right? This quantity Ra is called the Rayleigh number. As you can see, this is nothing but Grashof by Prandtl number. So we still have only two parameters. So either you can use the Rayleigh number or the Grashof number. Again, the Rayleigh number would involve, now the Rayleigh number also would involve the thermal diffusibility in the denominator. Okay. So we can now perturb the system and study the linear stability of this problem, because we have linearized equations. But we will make one more simplification. The one more simplification that we are going to do is to state that this Rayleigh number, remember, is buoyancy force to viscous force. Okay, so if buoyancy effects are small, okay, so how do we know this? Then that is, if Ra, the Rayleigh number is much smaller than 1, then we will simply ignore this term, ignore the gravity term. So what I'm essentially stating is that we will consider a situation where the Rayleigh number is very small. Okay. Now, when the Rayleigh number is very small, then buoyancy effects are negligible. This is the condition in which also the situation when Benard's experiments were actually done in the limit of very small Rayleigh number. And what this does is, if we ignore this term completely, then the right hand side of equation 13 essentially disappears. Okay, so we do not have a gravity term at all. There is still a coupling, but there is a coupling between the velocity, that is w hat, and the temperature theta from equation 12. But we'll also see that there is a coupling between these two variables, theta and w, also from the boundary conditions, because changes to the temperature fluctuations at the interface will lead to surface tension variations, and these surface tension variations will lead to velocity fluctuations. Okay, so now we have a simplified set of equations. The simplified equations that we have are PR del by del T minus del square of theta W, theta inverted hat is this, and finally I have the velocity equation del square of W hat is basically 0. Okay, so these are our equations 12 and 13. Okay, so what we have managed to do in this lecture is, let's quickly recap what we've done. We started with the non-dimensional form of the governing equations that we had done in the previous lecture. We had then considered the base state, and we found that the base state for the temperature field is just a linear variation in temperature. And we then perturbed the base state using simple linearized perturbations were considered. Now epsilon here is a small parameter. I forgot to mention that. Epsilon is an arbitrary small parameter. Okay. And it does not matter what exactly is physically the epsilon. Epsilon is just telling us that the amplitude of perturbations are small. It's an amplitude parameter. And we have the linearized equations. We started with 5 equations and 5 unknowns. We did some simplifications to reduce the number of equations. We got 3 equations and 3 unknowns. Then finally we did one more simplification and we got 2 equations and 2 unknowns, a coupled set of equations for the velocity perturbation and the temperature perturbations. Then we also said that buoyancy terms are negligible. We'll consider a situation where the buoyancy terms are negligible or Rayleigh number is small. One way in which this can happen is where the temperature variations are small. Another way to this can also happen is that the thickness of the film is also small. So remember, in the Rayleigh number and the Grashof number, you have a d cube term. So when d becomes small, then the Rayleigh number again becomes small. So if you actually consider thin films, then this term can be negligible. The gravity terms can be negligible. So now we have basically obtained the linearized equations for 2 variables, theta and w. Now in the next class, what we will do is we'll assume a form of the solution for these perturbation variables, theta and w, and then we will derive these are partial differential equations, remember. So we have time, we also have spatial derivatives, all the spatial derivatives, because remember this is a 3-dimensional problem. We have derivatives with respect to x, y and z. What we will then do is we'll reduce, in the next lecture, we will reduce them to coupled ordinary differential equations along with boundary conditions. Okay. So I'll see you around in the next lecture. Thank you.